Human beings appear to have been making their own ceramics for at least 26,000 years, subjecting clay and silica to intense heat to fuse and form ceramic materials. The earliest found so far were in southern Central Europe and were sculpted figures, not dishes. The earliest known pottery was made by mixing animal products with clay and baked in kilns at up to 800 degrees Celsius. While actual pottery fragments have been found up to 19,000 years old, it was not until about 10,000 years later that regular pottery became common. An early people that spread across much of Europe is named after its use of pottery, the corded ware culture. These early Indo-European peoples decorated their pottery by wrapping it with rope, while still wet. When the ceramics were fired, the rope burned off but left a decorative pattern of complex grooves on the surface. The invention of the wheel eventually led to the production of smoother, more even pottery using the wheel-forming technique, like the pottery wheel. Early ceramics were porous, absorbing water easily. It became useful for more items with the discovery of glazing techniques, coating pottery with silicon, bone ash, or other materials that could melt and reform into a glassy surface, making a vessel less pervious to water. Ceramic artifacts have an important role in archaeology for understanding the culture, technology, and behavior of peoples of the past. They are among the most common artifacts to be found at an archaeological site, generally in the form of small fragments of broken pottery called sherds. Processing of collected sherds can be consistent with two main types of analysis, technical and traditional. The traditional analysis involves sorting ceramic artifacts, sherds, and larger fragments into specific types based on style, composition, manufacturing, and morphology. By creating these typologies, it is possible to distinguish between different cultural styles, the purpose of the ceramic, and the technological state of the people, among other conclusions. Besides, by looking at stylistic changes of ceramics over time, is it possible to seriate the ceramics into distinct diagnostic groups, assemblages. A comparison of ceramic artifacts with known dated assemblages allows for a chronological assignment of these pieces. The technical approach to ceramic analysis involves a finer examination of the composition of ceramic artifacts and sherds to determine the source of the material and through this the possible manufacturing site. Key criteria are the composition of the clay and the temper used in the manufacture of the article under study. The temper is a material added to the clay during the initial production stage, and it is used to aid the subsequent drying process. Types of temper include shell pieces, granite fragments, and ground sherd pieces called grog. Temper is usually identified by microscopic examination of the tempered material. Clay identification is determined by a process of refining the ceramic and assigning a color to it using Munsell soil color notation. By estimating both the clay and temper compositions, and locating a region where both are known to occur, an assignment of the material source can be made. From the source assignment of the artifact, further investigations can be made into the site of manufacture. A ceramic is any of the various hard, brittle, heat-resistant and corrosion-resistant materials made by shaping and then firing an inorganic, non-metallic material, such as clay, at a high temperature. Common examples are earthenware, porcelain, and brick. The earliest ceramics made by humans were pottery objects, pots, vessels or vases, or figurines made from clay, either by itself or mixed with other materials like silica, hardened and sintered in fire. Later, ceramics were glazed and fired to create smooth, colored surfaces, decreasing porosity through the use of glassy, amorphous ceramic coatings on top of the crystalline ceramic substrates. Ceramics now include domestic, industrial and building products, as well as a wide range of materials developed for use in advanced ceramic engineering, such as in semiconductors. The word ceramic can be used as an adjective to describe a material, product or process, or it may be used as a noun, either singular, or more commonly, as the plural noun, ceramics. Ceramic material is an inorganic, non-metallic oxide, nitride, or carbide material. Some elements, such as carbon or silicon, may be considered ceramics. Ceramic materials are brittle, hard, strong in compression, and weak in shearing and tension. They withstand chemical erosion that occurs in other materials subjected to acidic or caustic environments. Ceramics generally can withstand very high temperatures, ranging from 1000 degrees Celsius to 1600 degrees Celsius. The physical properties of any ceramic substance are a direct result of its crystalline structure and chemical composition. Solid-state chemistry reveals the fundamental connection between microstructure and properties, such as localized density variations, grain size distribution, type of porosity, and second-phase content, which can all be correlated with ceramic properties such as mechanical strength sigma by the Hall-Petch equation, hardness, toughness, dielectric constant, and the optical properties exhibited by transparent materials. Ceramography is the art and science of preparation, examination, and evaluation of ceramic microstructures. Evaluation and characterization of ceramic microstructures are often implemented on similar spatial scales to that used commonly in the emerging field of nanotechnology, from tens of angstroms to tens of micrometers. This is typically somewhere between the minimum wavelength of visible light and the resolution limit of the naked eye. The microstructure includes most grains, secondary phases, grain boundaries, pores, microcracks, structural defects, and hardness micro-indentions. Most bulk mechanical, optical, thermal, electrical, and magnetic properties are significantly affected by the observed microstructure. The fabrication method and process conditions are generally indicated by the microstructure. The root cause of many ceramic failures is evident in the cleaved and polished microstructure. Mechanical properties are important in structural and building materials as well as textile fabrics. In modern materials science, fracture mechanics is an important tool in improving the mechanical performance of materials and components. It applies the physics of stress and strain, in particular the theories of elasticity and plasticity, to the microscopic crystallographic defects found in real materials in order to predict the macroscopic mechanical failure of bodies. Fractography is widely used with fracture mechanics to understand the causes of failures and also verify the theoretical failure predictions with real-life failures. Ceramic materials are usually ionic or covalent bonded materials. A material held together by either type of bond will tend to fracture before any plastic deformation takes place, which results in poor toughness in these materials. Additionally, because these materials tend to be porous, the pores and other microscopic imperfections act as stress concentrators, decreasing the toughness further, and reducing the tensile strength. These combine to give catastrophic failures, as opposed to the more ductile failure modes of metals. These materials do show plastic deformation. However, because of the rigid structure of crystalline material, there are very few available slip systems for dislocations to move, and so they deform very slowly. To overcome the brittle behavior, ceramic material development has introduced the class of ceramic matrix composite materials, in which ceramic fibers are embedded and with specific coatings or forming fiber bridges across any crack. This mechanism substantially increases the fracture toughness of such ceramics. Ceramic disc brakes are an example of using a ceramic matrix composite material manufactured with a specific process. Under some conditions, such as extremely low temperature, some ceramics exhibit high temperature superconductivity. The reason for this is not understood, but there are two major families of superconducting ceramics. Temperature increases can cause grain boundaries to suddenly become insulating in some semiconducting ceramic materials, mostly mixtures of heavy metal titanates. The critical transition temperature can be adjusted over a wide range by variations in chemistry. In such materials, current will pass through the material until Joule heating brings it to the transition temperature, at which point the circuit will be broken and current flow will cease. Such ceramics are used as self-controlled heating elements in, for example, the rear window defrost circuits of automobiles. At the transition temperature, the material's dielectric response becomes theoretically infinite. While a lack of temperature control would rule out any practical use of the material near its critical temperature, the dielectric effect remains exceptionally strong even at much higher temperatures. Titanates with critical temperatures far below room temperature have become synonymous with ceramic in the context of ceramic capacitors for just this reason. Optically transparent materials focus on the response of a material to incoming light waves of a range of wavelengths. Frequency-selective optical filters can be utilized to alter or enhance the brightness and contrast of a digital image. Guided lightwave transmission via frequency-selective waveguides involves the emerging field of fiber optics and the ability of certain glassy compositions as a transmission medium for a range of frequencies simultaneously, multi-mode optical fiber, with little or no interference between competing wavelengths or frequencies. This resonant mode of energy and data transmission via electromagnetic wave propagation, though low-powered, is virtually lossless. Optical waveguides are used as components in integrated optical circuits, e.g., light-emitting diodes, LEDs, or as the transmission medium in local and long-haul optical communication systems. Also of value to the emerging materials scientist is the sensitivity of materials to radiation in the thermal infrared portion of the electromagnetic spectrum. This heat-seeking ability is responsible for such diverse optical phenomena as night vision and IR luminescence.